Good afternoon and welcome to quantum computing today. And last week we started with the architecture chapter. So we will finish this today and then we will start looking into theoretical computer science. And next week we will look into selected algorithms and so forth. So last week, we started looking at how we can actually describe bits and qubits in terms of the framework we had established so far. So we did that, and we saw key to that is the 0 cat and 1 cat, and those are classic bits. And if we have qubits, we have a superposition of both. We described that, and we saw that complex numbers are our probability amplitudes, and eventually all of that is just a simplification of what we did in the previous week. We then looked at measurements. Again, it all gets very simple since we just have two basis states. And we looked at a few examples, how to normalize qubits, because we assume that these qubits are normalized. So the modulus squared of C0 and the modulus squared of C1 add up to 1. And we looked at a couple of very common notations. All of them just mean the same, but you will see them used throughout the literature. So we discussed all of that. And we also saw that the superposition really enables us to look at many states at a time when we combine multiple qubits. For example, in a qubit, we have 8 qubits. And we see that this leads to a massive exponential growth of possible states at a time. However, we are not really able to simulate that any longer in a classic computer for a certain number of qubits. We can still do this for a few qubits, but for way more, it doesn't really work. As we see, if we have 64 qubits that we would interconnect, it would lead to just way too many complex numbers a traditional computer would need to handle. And sometimes you see some supercomputers, they are used for simulating quantum systems, but most of that is just to help to better understand how quantum algorithms could be built. It's not really the solution to all of this, but rather an early step. And then once larger quantum computers become available, those learnings can be applied to a real quantum computer. But the simulations, they certainly don't lead to the desired speed up, and they're extremely limited in terms of the number of qubits we can look at. Then we saw very common notations as the tensor product of two qubits. We described that. We saw all of these notations here mean the same. Concretely, it means this one here. So we have two qubits combined. We have this aggregate system. We looked at some examples, and we also looked at what entanglement would look like in this notation. And then we started describing classical gates and established a mechanism just to describe classical gates in our linear algebra approach, like not and or, which are not quantum gates, but it helped us to move towards quantum. And then we described a couple of more sophisticated gates. We saw we can use the matrix multiplication to build more complex sequential gates. And for parallel gates, we need the tensor product. So all the math we did in one of the first lectures at the beginning of the term is actually helpful. We looked at a couple of cases like this where we need the identity matrix in parallel. We looked at a simple circuit and saw how we can describe it in terms of linear algebra. Then we started looking at reversible gates. And the reversible gates we look at, they're also quantum gates, but they also can be applied just to binary settings. So we started with the C0 gate, discussed it in detail, and it can be represented as a matrix, which is unitary, and therefore the operations are reversible. We also saw multiple C0 gates that would just undo what we wanted, and we looked at a universal gate, which is the Toffoli gate, and saw how it works and described it. And we saw why we need a third Toffoli gate here just to undo an unnecessary superposition, which we would have up here. So we discussed this in detail, and I told you we can also use this for a fan out. So we could copy one of the inputs and have it as two outputs. And there's another universal gate, which is the Fredkin gate, However, we didn't study that in detail because we looked only at one universal gate in detail, which is the Toffoli gate. Are there any questions from your side? Are you all okay so far? If you're okay, maybe send some green reaction. Otherwise, send a red reaction. And if you got any questions, please go ahead with the chat. I got some emails recently about students who still want to join the course. So the course is full for a long time. And I said this since the beginning of the term, you cannot sign up any longer. And you can only sit the examination if you're registered in the iLearn course. And if you have a team member submitting for the team, a group that presents something, I will carefully check if each group member is actually signed up for the course, and those who are not registered for the course yet uh, sign up in any way for the presentation through someone else, they will be not be able to present. So, because we have this limit that was initially 140 students and a few more eventually signed up, but we've reached the maximum and you can only sit the examination if you have joined the iLearn course. So, but I'll say more about the seminar presentations probably in 2 weeks. So in terms of the course, what we're doing in the next few weeks is, so today we're finishing architecture. We look at theoretical computer science. Next week, we will have a guest lecture. Concretely, Rolf Hoyer, who is the former Director General of CERN, he will join online and talk about quantum mechanics and applications of all of this at CERN, the European Organization for Nuclear Research. You are not just expected, you are required to attend that live lecture, and I will also send an update in the iLearn course that that next week's guest lecture is mandatory, and you need to join live because we have a very famous guest, so you need to show your respect and attend the guest lecture. But I'll say more about that via iLearn, via round mail. If you don't join next week, it could happen you just get unenrolled from the course. So this is a mandatory requirement for the course, and I would carefully look who has not attended in case next week's guest lecture is under attended. Yeah, so, and then next week we will also look at algorithms, and then in 2 weeks we finish the lecture by looking at concrete quantum computers and programming and applications, and then end of November we're done with the content and you can start focusing on the seminar presentations. But I'll say more about the seminar then in 2 weeks when we finish the lecture. But however, since we've done most of the content of the lectures already, please start looking for seminar topics, which is probably something helpful that you should start anytime in case you haven't started yet. And we finished with this slide last week. We looked at quantum gates, and we saw that some of the gates we had seen before are in fact quantum gates, like the NOT gate, the C-NOT gate, the Toffoli gate, the Fredkin gate, and the identity matrix, which is the identity gate. All of them can be represented by unitary matrices, and that's why they are quantum gates. Today, we will see a few more quantum gates. Concretely, we will see the Harder-Matt gate now, and that's something we had seen already a long time ago when we started with complex linear algebra. Today, we will explore it in greater detail, and for this, I will switch to my iPad. No. So the Harder-Matt gate is a super important gate in quantum computing, and what it does is it creates a superposition. Because if you have a quantum algorithm, you have certain inputs to the quantum algorithm, and those inputs will be classic values, 0 or 1. So just bit values that you're putting for those qubits. Because from outside, We access the quantum computer with classical values, and eventually we get classical values out of the quantum program once we do measurements. Measurements is something we'll also see in greater detail. We've seen measurements a few times, but we keep exploring them. Now, somehow I need to create superpositions because the quantum computing only enables us to do massive speedups if we have a superposition of qubits. So in one of the early steps in a quantum algorithm, we need to create superpositions. And then we keep working with those superpositions. And concretely, the Harder-Mott gate is key to that. And this Harder-Mott gate can also be represented as a matrix. The matrix looks like this, and each entry is multiplied by 1 divided by the square root of 2. And if you wish, we can also add some comments to this. So we just see from what we would map to what. But these comments, I don't think they're really necessary anymore in this course because we've done this now for a long time and you know what these comments are useful for. Now, how does this create a superposition? And concretely, if I take the Harder-Mott gate and I multiply it with 0 ket, we can see what happens. So we can just write this out in detail. 1 divided by the square root of 2. I don't put the comments here anymore, so it's 1, 1, 1, minus 1. This is the Harder-Mott matrix or the Harder-Mott gate. And we multiply this with 0 ket, which is 1, 0. So this one here, and the Harder-Mott matrix is this one here. Now we can multiply this and see what the result is. So what we would see is if we just leave this constant factor out, we multiply this one with this one and with this one, and the other entries anyway 0. So what we would get is 1, 1. And this one here, we have seen many times before, and we have seen how we can write it in many ways. So we could see 1 divided by the square root of 2 times 0 ket plus 1 divided by the square root of 1 ket, because we have the 0 ket here, and the 1 ket would stand for this. And we can rewrite this, and so that this would be 0 ket plus 1 ket divided by the square root of 2. So eventually, what we see here is that the 0 ket gets transformed to this one here, which is just an equal superposition of 0 and 1. So we create an equal superposition with the Harder-Mott gate. We can do this with the 0 ket. We can also do this with the 1 ket, just as another example. So Harder-Mott, and we multiply the 1 ket as a state. So 1 divided by square root of 2. And then we have 1, 1, 1, minus 1. And the 1 ket is this one here. So what we would get is 1 divided by the square root of 2, and we would get a 1 and a minus 1. So we have this 1 here and multiply it with here and here. And we can again rewrite this in a more common notation. So we have a 1 divided by square root of 2 times 0 ket minus, because we have the minus here, 1 divided by the square root of 2 times 1 ket. And we can rewrite this as 0 ket minus 1 ket divided by the square root of 2. So we would see that the 1 ket that we had here would get transformed to this equal superposition. So this is also a good summary of what we did so far with multiplying states with unitary matrices. Are you okay with these results here? Is this something that you feel comfortable with, or you would have been able to do on your own? But I see lots of positive reactions. Now we can continue with, we will see lots of other quantum gates, and we will not discuss them all in great detail here. We just look at different ones so you have an understanding of which quantum gates are available. And then when we start looking into concrete algorithms, for example, a lot of or some seminar presentations every year discuss concrete quantum algorithms in detail. You would have an algorithm that is composed of some of these quantum gates, and there are so-called Pauli matrices. And one is the X, and the X we have seen already, which is basically just the NOT gate. And there is a Y and a Z gate or a Z matrix. We will later see how we can interpret them from a perspective, what they do to the qubit. So the X is fairly easy. It just inverts or it just flips the two, or for a binary setting, it would just flip the bit. And if you apply it to a qubit, we would eventually just see that we change the complex amplitudes, and the Y and the Z matrices, they do something different, but we will see this later. Sometimes a different notation is used for X, Y, and Z, like a sigma X, sigma Y, and sigma Z. And the literature proposes other matrices like S, which looks like this, and T, like this. But I think you will see some of them once you look at concrete quantum algorithms. And we will see now very soon a notation, so we can also interpret what these operations would actually mean. Of the ones I have just looked at with you, there's also some identities that are proposed in the literature. So an X squared would be the same as a Y squared, or a Z squared, which is all just the identity matrix. And there are a couple of other identities. Feel free to prove them in case you want to see this. But I've also just taken this from the book, and it shows how these operations relate to each other. Now, when we keep looking at quantum circuits, because we know now lots of quantum gates, we build quantum circuits, and we usually start, as I said, with feeding in classic values. Then we create a superposition. Then we have lots of different operations in a quantum algorithm. And eventually, when we finish, we need to turn our quantum state into a classic value, because outside the quantum computer, we can only deal with classical values. So at the very end of a quantum circuit, we need measurements. And the measurements, we've seen this also when we looked at quantum mechanics, it collapses a quantum state. And here when we look at qubits, what we would get out from a measurement would be just a classic 0 or 1. And the measurement is also non-deterministic. We've seen this when we discussed about measurements. Just because you have a quantum state doesn't mean that if you run the same experiment again and you would have the same or related quantum state and you do a measurement, that doesn't mean you get the same result, because the measurement is also non-deterministic. So quantum computers are inherently non-deterministic, and we will see later that there is another effect called decoherence, which plays a very important role and adds even more uncertainty. So you probably wonder, what's the solution then to handle the uncertainty? Well, usually you would run the same algorithm, the quantum algorithm, many, many times, and you would get a distribution of the outputs, and then you would take the most likely output from the distribution. This still leads to a massive speed up, because if you have a quantum algorithm that gives you an exponential speed up and maybe you run the same experiment 1,000 times, this wouldn't really hurt. But this is something we will see when we look at concrete quantum computers and we run some experiments, and we'll see this in greater detail. Now, with qubits, we have the beauty that we just have two complex amplitudes, which are C0 and Z1. So this is just our generic qubit. psi ket, which is z0 times 0 ket plus c1 times 1 ket. And we said that the modulus squared of c0 plus the modulus squared of c1 needs to add up to 1. And it turns out that you can rewrite such a qubit in a different way. This is explained in the literature in greater detail how or why this representation is actually equivalent to this one here. But it's something we're not discussing in detail in the course. We just assume that it is that way. In case you want to verify this, please take a look into the book or into other literature. And what does this mean? So our psi ket can be represented as the cosine of theta times 0 ket plus, we say, e to the power of I times phi times the sine of theta times 1 ket. These two representations, so this one here and this one here, are equivalent. There are just a few more constraints because with this representation here, we can cover every possible qubit, and we assume that our phi is between 0 and 2 pi, so from 0 to 360 degrees, and our theta goes from 0 to pi half. Now, you wonder, what is this useful for? It's actually super useful because we only need two real numbers to identify a qubit, because we only need the phi and the theta, which are two angles. And with these two angles, we can represent the whole qubit, as we see here. Now, when we have these two angles, we can try to visualize a qubit. So this is very important. This only works for qubits. It doesn't work for more generic states, but we're now in the quantum computing part, so we only care about qubits here. And you can visualize this in a 3D sphere, which is called the Bloch sphere. And for the Bloch sphere, there's also an interpretation that our theta is the latitude and the phi is the longitude. And we can try to visualize this, and this is the Bloch sphere. Because all we need are these two angles, theta and phi. And with that, we can represent every possible qubit on the sphere. And we see there's a north pole, which is the 0 ket, and we have a south pole, which is the 1 ket. And in here, all we need to represent our concrete qubit is the two angles. And we have three axes. We have x, y, and z. And we will come back in a moment to these Pauli matrices we just saw in a moment, because they can be interpreted in here as well. Now, I think I'll just switch to this so I just go back to the Pauli matrices that we saw, which is x, y, and z. And we've seen what x does. X just changes the two, or it flips the two probability amplitudes. And what would happen is, if I have a 0 ket, it would turn it into a 1 ket. We've seen this before with the X gate. And Y and Z do something different. When we look at X, Y, and Z in this Bloch sphere, one can actually notice that these Pauli matrices, X, Y, and Z, they do a 180-degree rotation around the respective axes. So the X matrix, we saw it would flip a 0 ket to a 1 ket, which is just from the North Pole to the South Pole, or from the South Pole to the North Pole. Concretely, we do a 180-degree rotation around the x-axis. And it not only works for the 0 ket to a 1 ket, but also if we have some other state, we would rotate 180 degrees around x. And y and z also relate to these axes. So we have the Pauli Y matrix, which does a 180-degree rotation around the y-axis, and the Z matrix, the Z Pauli matrix, does a 180-degree rotation around the z-axis. So this is a graphical representation or interpretation of what x, y, and z do. And explain. So what I've just said is also written here, that the Bloch sphere allows us to visualize this, and we have a north and a south pole. One thing is also important with regards to measurement. So imagine my theta cat, my psi cat looks like this. It's close to the North Pole. What do you think is the most likely result of the measurement when I measure my psi cat? Would I get a 0 or a 1 cat? You can guess in the chat, because the measurement would turn my quantum state into a classic state. So what do you think if it looks like this? So most likely I would get a 0 a 0. Um, do you think this is the only possible outcome, or could we get a 1 as well? You can answer to the chat. And yes, we could get a 1 as well, even though here it's unlikely. But if I run the same experiment many, many times, and each time I do a measurement for a state that looks like this, then yes, sometimes I would get a 1 as well. So this is the Bloch sphere. There are other visualizations of qubits as well, because the Bloch sphere only works for 1 qubit. But in some of the literature, you find some other notations which are different to the Bloch sphere, but they could also help you to visualize with some diagrams if you have multiple qubits. But it's something you may see in some of the literature. There's not that one common notation aside from the Bloch sphere. But there are some interesting notations if you look at multiple qubits and you want to visualize them together. You may see this in, I don't think it's shown in the book of Janowski and Manucci, but there are other books as well. And they covered this. I think there's a book called something like Dancing with Qubits. I think that book shows some other notations as well, especially if you deal with multiple qubits at a time. So this is the Bloch sphere, and now what we can do is we can manipulate our qubit, so we can do a phase change. A phase change would be a rotation along here, as you can see, and the phase change changes obviously a qubit because we are changing the longitude. But in terms of the probability that we get a 0 after measurement, this doesn't change because we just rotate around here. So we're changing the longitude, but not the latitude. So it has no impact on what we would get after measurement. And the Bloch sphere, I've mentioned this, we can also visualize the X, Y, and Z Pauli matrices. And there's an example here. So, for example, if we have a 0 cat and we apply, no, not a 0 cat. So we have because that would be X, but here we rotate around Y, we will get a visualization like this. So this is just one way how we can visualize. And we always rotate by 180 degrees with the Pauli matrices. There are other matrices that allow us to do different dynamics. So we can have a phase shift, which we saw by a certain angle, and this matrix here would allow to do, it can be applied on an arbitrary qubit, and it's shown here also in detail what that operation would do. And eventually this matrix here is used as a phase shift, which is one common operation in concrete quantum algorithms, but we will start looking into quantum algorithms next week as well as in your seminar presentations. Today is only meant to show you a few more gates, and then when we see concrete quantum algorithms, we can just combine all of this. There are lots of other rotations. They are covered in the Janowski and Manucci book as well. In case you want to read this, go ahead. And there are other quantum gates. So, for example, in classic computer science, uh, an if-then statement is one of the most fundamental operations. When you write an algorithm, it turns out there is an equivalent operation for this as well in quantum computing. So, as a low-level operation, imagine you have a unitary operation U. You can turn this into a controlled U or CU, which would look something like this. So with this gate, based on X, I can turn N into a different N. So it's N inputs and N outputs, but I apply an operation here based on this control qubit here. And this would allow me to manipulate n qubits and change them into something, but I still have n output ones. And this could be represented as an n+1 qubit operation. So if I have an operation which is some unitary matrix, say A, B, C, and D, whatever this would look like, could be, say, some rotation we have seen before. Then this controlled U operation can be written like this. It's a 4 times 4 matrix with a 1 and 1 in the beginning of the diagonal, and down here the actual operation you want to apply. And then you have this controlled U. So based on the input or based on the control input, you would manipulate the n other qubits and turn them into some n other values. This construct here not only works for matrices of that size, but also for larger unitary matrices. So if you have multiple qubits combined, you can also use this here, and you may see this in some of the quantum algorithms that you're studying. Now, I've mentioned a term that is super important last week, which was something like universal quantum gates. And we saw that the Toffoli gate is universal. And I've mentioned all of this, but I just want to do a quick revision here, and because here it's also written in detail. In classic binary logic, for example, the set of an AND and NOT gate, this would form a set of universal logic gates. And the NAND gate itself would be just a combination of these two gates, and therefore the NAND gate is also a universal logic gate. Now, we have seen that the Toffoli and Fredkin gates, they are also universal logic gates. But they alone are not universal quantum gates, because the Toffoli gate and Fredkin, yes, from a logic perspective, the Toffoli gate is universal and the Fredkin gate as well. But these two alone are not universal quantum gates, because I need more than just a logic. I also, for example, need to create a superposition or do some rotations or whatever. So from a quantum perspective, the Toffoli gate alone is not universal, but from a classic logic perspective, it is. And there's one example in the literature, but it's just one of many examples, that the set of these three gates would be, for example, a universal set of quantum gates. So we have H, which is Harder-Matt, which creates our superposition, and we have C naught, which is the controlled knot. We've studied this last week, plus some phase shift by a certain angle, as we see here. If you combine these three quantum gates, you have a universal set of quantum gates. There are other ones, obviously, also somehow combining the Toffoli gate with others, but a Harder-Matt gate is something you would typically need from a quantum perspective, because you first have to create some superposition and then you keep working with the superposition. Now, the goal is later in this course, as well as in particular for your seminar presentations, that we build algorithms. So we take advantage of these gates and build something concrete that works. Something that is super important is each operation we use in such a quantum gate, in such a quantum circuit, they must be reversible. That's why unitary matrices are so important. But there's another limitation, which is called the no cloning theorem. This comes purely from quantum mechanics, yet it severely influences how you would write algorithms. In in a classic algorithm, so what you have done for the last few years, you may copy a variable quite often. So you copy a variable, then you manipulate the copy and so forth. All of this is very helpful, but in a quantum algorithm, that's not possible. So you cannot just copy paste a quantum state because in quantum mechanics, the no cloning theorem prevents you from doing this. The no cloning theorem, and it comes from quantum mechanics, but so quantum computing is also constrained to it, says that it is impossible to clone an exact quantum state. So it is impossible to make a copy of some arbitrary quantum state without first destroying the original. And this, I think, is one of the huge limitations that makes coming up with new quantum algorithms so difficult. Because in classic programming, in classic algorithm design, we copy stuff quite often. But here we cannot. So we are not able to make an exact copy. There are some suggestions how to make some approximate copy or something, but also that is limited if it works at all. But an exact copy of some arbitrary quantum state is not possible. And if you measure first, you would turn the quantum state into some classical state, either 0 or 1. And when you take that, you can obviously copy the classic state, but you cannot infer back what the quantum state was based on what you have measured. So big limitation. So copy paste is not possible. We can obviously move, if I have a quantum state, I can move it from one qubit to another qubit. That's obviously possible. Moving is possible, but copying is not. And when we started this course a month and a half ago, I asked you to read this book chapter. Who of you actually read it? I'm just curious to see how many read it and maybe how many still remember the key message. If you have read this book chapter, send some reaction, because I said in the beginning of the term that this was actually important. First in this book chapter, and maybe now that most of the content in this course is already done, you should definitely read this book chapter again, even if you have read it before, because I think it will just help you to understand some stuff better. There's an introduction about the history of quantum computing. There are some foundations. We see what quantum states look like, which you see here. We see the Harder-Mott gate, and we see why quantum parallelism is so important. Entanglement, measurement. Next week, we'll look at concrete quantum algorithms. So this is about to come. Today, we discuss the theoretical computer science part. We will also see concrete architectures in 2 weeks. But the challenges is something we have already started. I've said coming up with new quantum algorithms is difficult because you need to think in these very low-level operations. I've mentioned decoherence, which we will also see in greater detail. And something that you, because of quantum mechanics, would also probably struggle with is debugging quantum programs. Because debugging is something very common in classical programming. Because in classical programming, we debug all the time to see why an algorithm does not work, because we deal with classic values. Yet debugging a quantum program doesn't really work, because I cannot just look at the quantum state, I need to measure it. And once it's measured, it's gone, it's collapsed. So I think this is also a huge limitation that we face in quantum mechanics, for which there's simply no solution because of nature. That's something that a lot of people actually don't talk about. The no cloning theorem comes on top. I don't think I have specifically mentioned it in here, or maybe I have, I don't know. But it's part of the challenge of coming up with new quantum algorithms. So please read this chapter again, because I think you will understand a lot of this now better, since we have finished like more than 75% of the lecture content already. Now, when we looked at the Toffoli gate last week, and I'm just going back like 20 or 30 slides to the Toffoli gate, we saw that we can use the Toffoli gate for a fan out, that we copy Y. This only works for binary states, so for classic logic. This does not work for quantum states, because it would be a violation of the no cloning theorem. So very important that this Toffoli gate here for fan out works for classic values, but not for quantum states. So this fan out that I proposed here last week is actually not a limitation, or actually not a violation of the no cloning theorem. And I've also explained this here. So this no cloning theorem is actually something that is key to a lot of seminar presentations every year. Quite some students every year give a presentation on quantum key distribution, in particular the students who study cybersecurity. This is not a recommendation that like 50 groups will present quantum key distribution, yet maybe some of you, especially the ones from cybersecurity, are interested in quantum key distribution, and here the no cloning theorem plays a very important role. If you want to learn more about the no cloning theorem and its consequences, it's explained also in the Janowski and Minucci book and in the Aronson book. Quantum computing, since Democritus, I mentioned this book when we started with the course. I don't know if any one of you got the book, but there are a couple of pages that also address the no cloning theorem. Now, we will finish now this chapter by looking at something that we call mixed states. And so far, all the quantum states we have looked at, they were known as pure quantum states. We will now look at mixed states, which are not pure, and we will see why they are important to quantum computing. And all our pure states that we saw so far, they can be described by a single ket. So a single ket is just a vector. And we've seen all the states so far, they could be described by that. But when we have these quantum states, we can actually put something on top of it, and we come to mixed states. And this is something I will show you now as the last part of this chapter. And I will largely develop this with you also on the whiteboard. So, what is a mixed state? We can have an example of a mixed state. Say a mixed state could have, or we can see a mixed state as a statistical ensemble of pure states. So one example of a mixed state could be that we have a half probability of 0 ket plus 1 ket divided by the square root of 2, and a half probability of 0 ket minus 1 ket divided by the square root of 2. So we would have a statistical ensemble of these pure states. We will first see how we can describe this, and later we will see what this is actually useful for. So we can, something that is key here is a so-called density matrix to describe this. And a density matrix can be derived the following way. We can call this, for example, rho, and rho is a sum of a probability PS, which is the fraction of the ensemble in each pure state, And then we have these pure states, which we call psi s ket, and we multiply this with psi s bra. So we have the ket here, and it's bra. And do you still remember what's the relationship between ket and bra? We discussed that, I think, 2 weeks ago. Maybe just send me a thumbs up or thumbs down if you still remember the relationship of how ket and pra relate to each other. And maybe some more answers. Also, if you don't remember that, uh, don't be ashamed. Just let us know because that means you need to spend also more time on the revision. Um, so this is a sum, and we have this probability PS, which is the fraction of the ensemble in each pure state, and this is the pure state, our psi s ket, and we have this outer product. So this is the outer product of psi s ket times psi s bra. We will see in a moment how they relate to each other. Now, why is this density matrix important? Because it encodes all the information that could ever be obtained from some probability distribution over quantum states by first applying a unitary operation and then measuring the state. We can take a look at one example of such an outer product. So example of outer product. We've worked a lot with inner products, yet the outer products, they're just the other way around, and they don't lead us to a single value, but actually to a matrix. So we could say we have our psi ket, and psi ket is 0 ket plus 1 ket divided by the square root of 2. And now we want to know um, what's the outer product. So we said psi ket times psi bra. So psi ket is up there, 0 ket plus 1 ket divided by the square root of 2. And the relationship of ket and bra was that one was the adjoint of the other. So we have this is our psi ket. Just put this here as an explanation. So this was the psi ket. And the psi bra is just the 0 ket plus 1 ket divided by the square root of 2. We take the adjoint. So this is the relationship of these two. So this is our psi bra. And we can just turn this now into vectors. So this, and we move the constant factors inside. So 1 divided by the square root of 2 and 1 divided by the square root of 2. And don't forget, obviously, this adjoint. So we put the adjoint here, just highlight it. And then this is 1 divided by square root of 2, 1 divided by square root of 2. And remember the adjoint. So the adjoint transposes this vector, and it also calculates the complement of the complex numbers, but these are just real components of the complex number. So the values don't change, but we have the 1 divided by square root of 2, 1 divided by square root of 2, and eventually this one here would just transpose this column vector into a row vector. So, and now it's your task that you multiply this column vector and this row vector, and once you have the solution, please send it to the chat. And I'm curious to see what you think the answer would be, maybe without looking at the slides. So I'll wait for you, and once you think you have an answer what this outer product here could be, let me know. It's not the inner product, so the inner product would just lead to a scalar value, but this is the outer product, so it leads to a different structure. And since I haven't seen any answers in the chat yet, maybe you can tell me if you think you get the solution, and I'll wait for you that you send your answer. Maybe then send a thumbs up. If you think you don't see the answer, maybe send a thumbs down. So maybe some more answers would be just some, well, some reactions now you don't see it. Fine. So in this outer product, so if we flip these two structures, it would just be the inner product and would be a scalar value. But here it's the outer product. So what this actually leads to is just a matrix, a 2 times 2 matrix. And the first entry would be the product of this and that. So 1 divided by the square root of 2 times 1 divided by the square root of 2 would be a half. And it turns out for the next entry, we would take this and that, which would be a half, and eventually the other entries are also a half. So it's a 2 times 2 matrix. It's the outer product, not the inner product. Now, what does this density matrix mean? I've mentioned it before that it allows us to encode all the information that, or well, next we are actually building the density matrix. We're not there yet. But now we have done for one element, we have done this outer product. The goal is now we calculate the whole density matrix. So we could say, as from before, because my example from before was that we go back to this one here, that we have a half probability of 0 cat plus 1 cat divided by the square root of 2, and a half probability of 0 cat minus 1 cat divided by the square root of 2. For this first part now, for the one I put in blue, we have just calculated the outer product. And now for the next one in red, we also need this outer product. And it turns out if you calculate this for 0 cat minus 1 cat divided by the square root of 2, you would also get an outer product, which is a half minus a half minus a half and a half. Feel free to try this out at home. Then we have the outer product just from above for 0 cat plus 1 cat divided by the square root of 2. And we said that we have a half probability for each of them, so a half here, a half here. And we just calculate this, and eventually this is just simple math. So we have a half factor here, and we have these elements here. They would just cancel each other out in these two respective locations. And then we have these factors, and eventually this would just be a half, 0, 0, a half. And this is the density matrix of such a statistical ensemble. So I'm writing here, this is the density matrix. And before we called this density matrix rho, and I've put this here. Now, what does this density matrix actually mean? So what does the information that is encoded in here mean? Actually, a consequence is of these 2.5 in here, that there is no measurement you can ever perform that would distinguish this mixture from a half probability of 0 cat and a half probability of 1 cat. Now, what is this actually useful for? These mixed states are super important in quite a lot of algorithms, and I'll show you this now in the slides. So we saw this definition. We've calculated one outer product. we've calculated this density matrix, and all I said orally with some explanations is also in here. Now, this density matrix can also be thought as a way of using a one particle formalism to describe the behavior of many particles for which we give a probability distribution or an ensemble of states that these particles can be found in. Now, we'll look at some applications now, and when you look at some algorithms on your own, also for your seminar work, most likely you will come across all of this again. Now, some examples when mixed states could appear is, say, in quantum mechanics, there are two common situations. For example, when you prepare the system and this preparation of a system is not fully known, then you must deal with a statistical ensemble of possible preparations. But it could also happen that when you want to describe a physical system which is entangled with another, because its state cannot be described by a pure state. So there's also a link to entanglement. This is all also related to quantum decoherence. So what is quantum decoherence? I mentioned it, I think, a few times, and we will see it a lot when we look at concrete quantum computers. We saw one source of uncertainty is measurements, because the measurement turns a quantum state into a classic state, which is uncertain. But as you run computations in a quantum computer, you also add uncertainty, because your quantum computer or your quantum system starts interacting with the outside environment. Now, when your quantum system starts interacting with the environment outside the quantum system, then it loses its purity. And that's called quantum decoherence. So the longer you run a quantum algorithm, the more it decoheres, so it loses coherence. And as a consequence, you add more uncertainty. And then your outcome will be less and less good. The longer you run, the more decoherence you get. So something you would aim for in a lot of quantum algorithms is to actually reduce decoherence by trying to have very short quantum circuits so the quantum experiment does not take very long. And then you try to run this experiment many, many times, because you add uncertainty through decoherence and you add uncertainty through the measurement. So you run the same experiment many times. When we look at concrete quantum computers in 2 weeks' time, we also could think about what you could actually do to reduce decoherence. And there are some vendors that aim to build quantum computers that don't suffer from decoherence, but so far all of this is, I think, largely theoretical. And the quantum computers we have today, they suffer from decoherence, and it's unclear if you can actually get rid of it. With decoherence, essentially, your quantum state also loses its purity and turns more and more into a mixed state. So this is the essence of the link between purity or mixed states and quantum decoherence. And in 2 weeks, we will see how we can actually reduce decoherence, if it's actually possible to build quantum computers without decoherence. But currently, what we see so far in this course is we add uncertainty. Now, there are applications for mixed states. For example, in quantum communication, there are some scenarios, some practical scenarios, in which the state of your qubits cannot be written down as a linear combination in a given basis, but you must express this in terms of ensembles of multiple states. And there's one example in quantum communication. So for example, Alice wants to send to Bob the state plus cat. And because there is noise in the communication channel, there is some chance that the phase of that state plus cat could flip with some probability p. So Bob could end up with a certain probability to get the flipped state minus ket, um, or with the desired state, which is our plus ket, the one we aimed for. And that would be probability 1 minus p. So p would mean the probability of flipping and 1 minus p for not flipping. So the state that Bob gets is either plus ket or minus ket, but not a quantum superposition of the two. And if we want to know what will happen to Bob's qubit after, for example, he applies some gates and performs a measurement, we have to consider both of these cases separately. And this is where the mixed states or the density matrix come into play to describe that kind of setting. So maybe this is something that also some of you wish to explore in a seminar presentation, quantum communication. Every year, some students pick something like this and explain such a problem in greater detail. But these are just recommendations. Please don't, I would not be happy if 30 groups try picking something like this. Please do your own readings and try to come up with your own seminar presentation. Because if too many groups aim to present the same, we have to reassign different topics because I don't want to hear the same presentation 30 times in mid-January. It turns out if you want to try out some of this with code, so what I have just shown you, there's a very good library. It's called Qiskit. And Qiskit is a library for quantum computing from IBM. And we will quickly look at it together. And so when we look at concrete computations on a quantum computer in 2 weeks, we will also look into Qiskit. And Qiskit can allow us to simulate some quantum systems at the scale of what's possible in a traditional computer. But you could also switch your code to a real quantum computer, and it would run, for example, on a real quantum computer that IBM makes available. So they have some available through the cloud. And with Qiskit, you just write eventually Python code, and what you can do is you write in Python your quantum algorithm. So you describe that you have, for example, a Harder-Matt gate, whatever, and all of this would get turned eventually into code that is run on a real quantum computer, or it's run in a simulator. But what you do is you write code in Python, yet you still need to think in these very low-level settings, so in these low-level operations. And in case you want to try out some of the stuff I have talked about in this course, take a look at Qiskit. It's just a Python package that you can install, and you can run all of these computations. You can visualize qubits on the Bloch sphere and so forth. And we'll see some example code in greater detail also in 2 weeks when we look at concrete quantum computers on which we can run all of this. Now, I know this course so far has been lots of theory, and some of that was not easy to get. I fully understand this. It's a very advanced course. There's a very interesting website. It's called, so the domain is quantum.country. And I really like that website, and we'll look at it now together. I've already opened it. So if you open quantum.country, what you will see in there are 4 big so-called interactive essays. Has any one of you seen quantum.country before? Maybe just let me know with a thumbs up or thumbs down if this is something you have seen before. It's something I came across a few years ago, and you can open the first essay, which is Quantum Computing for the Very Curious, and you can scroll down, you get very good explanations of what quantum computing is about and the motivation, and then you're asked questions. So how many dimensions does the state space of a qubit have? 2. And you can click if you remember this or you didn't remember. And then we could also ask the state of a qubit is a 2-dimensional vector. And there are things you may not remember, and then you can open this essay again in a week, in 3 weeks, or 3 months, or in a long term, and you will be presented questions again, and mostly those questions which you did wrong. Sometimes some you did right just for revision. So this is a very smart way of learning, and you can scroll down here and you see qubits. So it starts with qubits and quantum computing, and what some gates are. So they take a bit of a different direction because we started first with the math in detail. We started then with quantum mechanics and then went into computing. This essay here starts directly with computing. So they get more to the specialized one. We started with the more generic part first. And you see various gates like the Harder-Matt gate or some idea what quantum computing is about. Some of these calculations. They're obviously not presented in that detail that we discussed it. And here we see the relationship of a cat and the bra, by the way, the controlled NOT gate, which we have seen. So this could be really complementary for you, and you will see what a quantum circuit would look like. This is something we will also see when we look at quantum algorithms in a few weeks' time, or next week already. So feel free to read this and you ask questions. And if you remember stuff, fine. If you remember some stuff, if you don't remember some stuff, it's fine. Just go back a week, 3 weeks, 3 months later for further revision, and you see some example circuits. So I said this essay started with the more specialized stuff. If you want to understand or study quantum mechanics in more detail, like what we have done first in this course, feel free to check this essay as well. So there's a quantum mechanics distilled. I think most of what is covered in this essay we have covered as well. Obviously, there are some things we covered that this essay does not cover, and the essay may cover a few details that we have not covered in the slides. Yet, if you do some extra readings in the book, I think all of this is something you should have seen. So we saw that quantum states are eventually a vector of complex numbers. We've seen the dynamics, so using unitary matrices. We skipped the details of measurements because we mainly care about them from a qubit perspective. We saw how we can combine systems by using the tensor product. So you see, it's actually a good summary of what we did, yet we didn't do the details of the measurement. And this could be very helpful. There is an essay about the quantum teleportation. It's something we have not discussed in this course, but maybe it's interesting for a seminar presentation. And we will study next week an algorithm, the Grover algorithm. That was one of our motivations when we started with this course in the beginning of October, which is the Grover algorithm or the quantum search algorithm. This one is also explained in here in this essay, and you can study this in maybe 2 hours or something and do some coursework or some quizzes. So in case you're curious about the details of the quantum search, take a look. So I find these quantum.country essays super helpful. Let's see if any further essays would appear with them in the future. I think now when I started with this, one of them was missing. I think the quantum teleportation only came later, but so far it looks quite stable that most likely they won't be adding new essays anytime soon, but maybe they will. So it's something I personally like very much. Maybe you want to spend some time on this on the weekend. Now we have looked at this one here. So we're done with the architecture chapter. And as you see, we have finished 5 chapters and actually most of the slides, because some of the materials we'll be looking at now is in other resources. And yet these remaining 4 chapters, they are all smaller than the chapters we have done so far. So most of the lecture content is done, but we are getting more and more into computing. And concretely, we will look today into theoretical computer science. And next week, we have the guest lecture of Rolf Hoyer, and then we study selected algorithms. And in 2 weeks, we finish the last 2 chapters. And then you should also be fine with picking a topic for your seminar presentation. So, theoretical computer science. We hear a lot about quantum computers turning evil, quantum computers being super powerful, more powerful than traditional computers. But what are the limits? And on the news, you hear a lot of stuff that there were no limits for quantum computers. It would all turn evil, and that quantum computers would be generally better than traditional computers. So I think what's important is to actually look at the theory. And since there's a very good essay, I have not created a lot of slides about this. And I asked you to read an article that was written by Scott Aronson. So the article is called The Limits of Quantum. And this article is from like 2008. The theory has not changed because the theory is solid. What has changed since 2008 is that we got more or that we actually got real quantum computers. They're still limited, but the theory obviously does not change. Who of you actually read The Limits of Quantum? Maybe thumbs up, thumbs down. So, and for the ones that have read it, maybe you want to turn on your mic and tell us a little bit what what you learned in this article and if there was anything interesting in it. You can turn on your mic and maybe just talk to us and not just write in the chat. So I would be very happy if anyone shares some insights. Well, with there not being any contributions, you all were supposed to read it. I will quickly provide you with an essence about this, but you're still supposed to read this in case you have not, because remember, there's also a Q&A session after the presentations, and we could cover everything discussed in class. So this book chapter or this article here addresses what the limits of quantum computing are, because there are some news on the internet that, for example, quantum computers could rapidly solve certain problems, including all the problems that we call NP complete. So what is NP complete? We will see this very soon, but this was a common mistake in the news, and there's a lot of misunderstanding, or was already at that time, what quantum computers were about. So the beginning of this chapter starts with the theory that sometime in the 80s, quantum computers were proposed, and then there is a quick overview about what quantum computing is about, what qubits are, and then certain complexity classes are addressed. So one complexity class is, for example, P. P means that the problem we want to solve can be solved in polynomial time. Are you all familiar with these complexity classes? P, NP, NP complete. Maybe thumbs up or thumbs down if this is something you have seen. It should have been discussed in your intro to computer science in your first semester or something. So the problems in P mean they can be solved in polynomial time, like n, n squared, n to the whatever. And even though this may take very, very long for a large n, it's still much easier to solve than other problems. And there are, for example, there's NP, and solving the NP problems is much harder, but you can verify a solution if it's correct in polynomial time. So solving may be very, very complex. Verifying if a solution is correct runs in polynomial time. And then there is NP complete, which we will see soon. And there is a long-standing question in computer science if these two classes, P and NP, are the same. This is an open question in computer science, whether these two classes are the same. If they really were the same, that would have dramatic consequences on a lot of computational problems. There has been no proof whether these classes are the same or if they are different. Yet, I think there's a lot of evidence that these two classes are in fact different, but it has not been proven. And there's a whole list of on the internet of people who have tried to prove whether P and NP are the same or whether they are different. When I did my PhD in a different lab in our institute, there was also a guy who tried to prove then he claimed P and NP were actually the same. And he was so sure, but there were some fundamental mistakes in the very beginning in the assumptions that he had made. And since then, he appears on some list on the internet that he tried to prove and it didn't work out. So this is a highly contested topic. And what I find very helpful in here is there are certain problems that computers can solve efficiently. Their NP problems are the ones that may take very long to run, but um, verifying is fast. And then there's a set of NP complete problems, and those are a subset of NP where if you were able to efficiently solve one of them, then all of them could be solved very efficiently. This is explained here in detail. And what I find most helpful in this paper or in this article is this figure. So assuming that P and NP are different, you can use this Venn diagram here. So we have the set of P, the problems that we can solve very efficiently in polynomial time. For example, problems from graph connectivity, matchmaking, testing if a number is a prime. Then the NP problems, for example, graph isomorphism, assuming that P and NP are different. And there are certain NP problems, so it's a subset of NP, like box packing, map coloring, n times n, Sudoku, traveling salesman, and so forth. There's also a class P space. It's also mentioned briefly in this chapter, so that you need polynomial space in your memory to solve these problems. It's a bigger class. And now where do quantum computers come into play? There's a class called BQP, and those are the problems that can be efficiently solved by a quantum computer. For example, factoring, so cracking today's encryption could be, we could have a massive speed up. And obviously BQP includes whole P, but it is more problems. And for example, the discrete logarithm. So the Grover algorithm, the quantum search that we saw, is actually in the classic search is in P because we have n O of n time to solve the black box search. But with a quantum computer, it would be O of square root of n. So BQP includes all the P problems plus some more, and probably the um, most the one with the biggest impact eventually will also be factoring, so we can solve um, prime number decomposition much faster, because that's what modern encryption is based on, and it takes nearly exponential amount of time to solve it. And with a quantum computer, so with Shor's algorithm, we could solve this much faster in a much better complexity class. It's something we will see next week when we look at quantum algorithms. So this plot here is, I think, the most important part in here. The Grover algorithm is also briefly explained. The Shor algorithm is explained in here. So if you read this article, it can be a very good summary. The ones who have read it, did you find this figure here helpful? Maybe just let us know. And I see some positive responses. So I found this figure here very helpful. It's probably the most helpful thing in this article. And there is some speculation if there could be something more advanced than quantum computers. But I think that's also largely speculative. So maybe if you read this, you can safely stop at page 6, and our last 2 pages are only for the super curious ones. This was this chapter or article, and you're supposed to read it and understand it. Also, with regards to the seminar presentation Q&A, the article here covered the BQP class. It turns out there are more classes than BQP with regards to quantum computing, and they are discussed in great detail in the Janowski and Minucci book. There is BQP, there is BPP, the NP and P, but there's also the complement NP. So feel free to read this. In the whole chapter 8 in the Janowski and Minucci book covers complexity classes. And there are a couple of more ones that are interesting, like BPP, ZQP, EQP. Maybe some of that could also be interesting for a seminar presentation if you are more into theoretical computer science and want to share with us some of the findings in the book. Uh, just as another recommendation the towards the seminar presentation. Today's lecture is a bit shorter than last week because I'm also not feeling too great. I need to admit, I got a virus yesterday and still was able here to teach for 1.5 hours. But I think there was quite a lot of new theory, and you should also read this article in case you have not read it, as well as this book chapter that I have already proposed in the beginning of the term. And next week, be punctual for Rolf Hoyer's guest lecture. I will also send a round mail in the iLearn course. And Rolf will give his guest lecture. And after his guest lecture, we look at selected algorithms. And then in 2 weeks' time, we do the 2 remaining chapters. And you've also seen the timeline for the seminar presentations, but I'll say more about this also in 2 weeks. So if there are no questions, we are done for today. And I wish you a great weekend. See you next week. Bye bye.